pleasure to present Hess Law of Constant Heat Summation, what is also known simply as Hess Law. So the law is named after a Swiss-born Russian chemist and physician by the name Germain Henry Hess. Henry was born in 1802 and died in 1850 at the age of 48 years. This law was published in the year 1840. Let us move on to statement of the law. Hess Law states that, and I quote, "The heat change in a given reaction depends only upon the initial and final states of the system and is independent of the path followed." Close quotes. So simply put, we are saying that regardless of the multiple stages or steps that a reaction may have, the total enthalpy change for that reaction is the sum of all the changes. To put this statement into perspective, let's have a look at this situation. Carbon may be converted to carbon 4 oxide either directly by burning carbon in excess oxygen or by way of carbon 2 oxide, where we shall burn carbon in limited supply of oxygen to get carbon 2 oxide, which we then oxidize further to give carbon 4 oxide. So what we are saying is there are two possible routes which can be followed from carbon to carbon 4 oxide. Now route 1 involves a situation where we burn carbon in excess oxygen to give us carbon 4 oxide directly. So let us assume that the heat change involved in this first route is X kilojoules per mole. The next route, that is route 2, would be we first burn carbon in limited supply of oxygen to give us carbon 2 oxide. Now, as we balance this equation, we need to appreciate the fact that as we form carbon 2 oxide, we need to maintain 1 mole of it being formed here. And for purposes of balancing, we are then forced to use a half on oxygen so that we maintain 1 mole of carbon 2 oxide being formed. So let us assume that this time the heat change involved here is Y kilojoules per mole. And then once we obtain our carbon 2 oxide, we oxidize it further by burning it in more oxygen to give us now the final product which we needed, and this is carbon 4 oxide. Again, as we do this, we need to maintain 1 mole on our product here. So we are again forced to balance with a half on oxygen. Let's assume that the heat change involved here is Z kilojoules per mole. Now, these two routes that we've just obtained from the two possible paths that lead us from carbon to carbon 4 oxide may be represented in either an energy cycle diagram or an energy level diagram. So we begin with an energy cycle diagram, and for this illustration I will exclude oxygens in my cycle. So from carbon I can obtain carbon 4 oxide directly, and we've agreed the amount of heat energy involved here is X kilojoules per mole. If I don't want to go that direct route, I can first obtain carbon 2 oxide, which I oxidize further to my final product of carbon 4 oxide. So here we have Y kilojoules of energy, and here I have set kilojoules. That becomes our energy cycle diagram. Let's now look at the energy level diagram. So for the energy level diagram, we shall assume that we begin with carbon being burnt in limited oxygen, and we've agreed we shall balance with a half on oxygen to produce carbon 2 oxide. This reaction normally produces heat, so it is exothermic, and the delta H is negative. So at this point we shall produce our carbon 2 oxide, which we can burn further in extra oxygen to give our final product of carbon 4 oxide. Take note that as you burn your carbon 2 oxide, you also produce heat, and therefore the reaction is exothermic, the heat change is negative as well. So from here, this is our Y kilojoules, this is our Z kilojoules, but if I needed now the amount of energy involved for the direct route, I'm able to get it from here, and that would be my X kilojoules of energy. So those are the two diagrams that we can draw to represent the two routes that we've just talked about. First one up here being called energy cycle diagram, and then we now have the energy level diagram. Now, according to Hess law, and I'm going to use my energy cycle diagram to explain, the initial state of the system is here. This is where we have initial state, and all the routes lead to carbon 4 oxide. So this becomes our final state. By Hess law, the amount of energy spent or released for the direct route is the same as for the indirect route. So we can conclude that X is being given by the summation of Y and Z. So according to Hess law, the heat of reaction in going from carbon to carbon 4 oxide is the same whether the change is achieved directly or through a series of steps as discussed above. So we can conclude from our two diagrams that X is given by the summation of Y and Z. That is Hess law in simple terms. Let us now move on and see where or which situations do we apply the law. That is applications of Hess law. So when it comes to applications of Hess law, we realize that Hess law is very useful in calculating heat changes which may not be possible to determine directly. For example, in our above example, if we are given that x is y plus z, if we have x and y only, it is possible to find the third constant. So let's take a look at an example here. So we may be asked to determine the enthalpy of formation of carbon 2 oxide when we are given only the enthalpy of combustion of carbon and enthalpy of combustion of carbon 2 oxide as 393 kilojoules per mole and 283 kilojoules per mole respectively. Now, what are the steps? So, the first step, if we are asked to find enthalpy of formation of carbon 2 oxide from the two enthalpy changes given, the first step is to write thermochemical equations for any enthalpy change mentioned in the question. In our question, we have mentioned 3 enthalpy changes. That is enthalpy of formation of carbon 2 oxide, enthalpy of combustion of carbon, and enthalpy of combustion of carbon 2 oxide. So let us go ahead and write their thermochemical equations. Enthalpy of formation of carbon 2 oxide means that we shall form carbon 2 oxide from its constituent elements. So here we are. And as we write this equation, we realize that for the equation to hold as enthalpy of formation, we must form only 1 mole of our product. For that matter, we shall balance with a half on oxygen. Now, this enthalpy change has not been given in our question, so we shall denote it with X kilojoules per mole. Moving on to the other enthalpy changes mentioned, we have enthalpy of combustion of carbon. Enthalpy of combustion of carbon would mean that we burn carbon in excess oxygen to get now the higher oxide, and that is carbon 4 oxide. The equation is already balanced, but for it to qualify to be a thermochemical equation, we must have its delta H indicated on the right hand side. That value has been given as 393 kilojoules per mole, but you realize when you burn carbon, it produces heat. Reactions that produce heat are exothermic, and delta H for exothermic reactions are usually negative. So that becomes our thermochemical equation for enthalpy of combustion of carbon. We end with enthalpy of combustion of carbon 2 oxide. And we know when you burn carbon 2 oxide in excess oxygen, you get carbon 4 oxide. As we balance, enthalpy of combustion dictates that we burn only 1 mole here. So balancing would involve a half on oxygen. The heat change has been given as 283, and we know when you burn carbon 2 oxide again, you produce heat, so we shall put a negative on 283 kilojoules per mole. That is our step 1. Now, in step 2, out of these 3 thermochemical equations, we are supposed to get one that is supposed to act as the main root to our energy cycle diagram. This equation that acts as the main root, we are able to derive the other equations from it so that we complete our cycle. Let us see how that is done. In step 2, we will identify from the 3 thermochemical equations that we have, we will identify the thermochemical equation which can act as the main root from which all the other thermochemical equations may be derived. We shall then use this to draw either an energy cycle diagram or an energy level diagram to represent all the equations above. We then go ahead and use the diagram to determine the enthalpy of formation of carbon 2 oxide, which was asked in the question. So once again, let us copy our three equations from our step 1. We had enthalpy of formation of carbon 2 oxide, and here the amount of heat involved wasn't known. Let's call it X. We had the enthalpy of combustion of carbon, and the amount of heat involved here was given as negative 393 kilojoules. Finally, we had the heat or the enthalpy of combustion of carbon 2 oxide, and the amount of heat involved for the change was negative 283. So once we have these three, the next thing a candidate should do is to identify one that can act as our main root from which the other two can be derived. And you agree with me that that equation is equation 1. So equation 2 being carbon can be derived from here, and equation 3 having carbon 2 oxide can be derived from this end. If you looked at equation 2, for example, there is carbon, yes, for equation 1, but you don't see any carbon 2 oxide here. So this may not be a main root. The same to equation 3. So we shall go ahead and use equation 1 to draw our energy cycle diagram. For this part, I'll exclude the oxygens. So from carbon to carbon 2 oxide, that is X kilojoules from equation 1. Equation 2 I can obtain from here going down to carbon 4 oxide. There we are. Amount of energy involved is negative 393. And from equation 3, I can get an arrow going down from carbon 2 oxide to carbon 4 oxide. Amount of energy involved is negative 283. So this becomes our energy cycle diagram. Candidates should take note, this is where we are originating. This is our initial state of our system, and all the arrows lead to this, which is now our final state. So by Hess law, we will then get X as follows. The enthalpy of formation of carbon 2 oxide, which we are asked, X, if you add to negative 283, this is our root 1, should give the same amount of heat energy as root 2, negative 393. So from here, our enthalpy of formation of carbon 2 oxide is given by negative 393 added to 283. If we add 283 both sides to eliminate negative 283 on the left hand side, this gives us a value of negative 110 kilojoules per mole as the enthalpy of formation of carbon 2 oxide. Very, very easy, and it is Hess law that has enabled us to get that. We are through with our simplified series where we've looked at Hess law. We now invite you to join us in our next video where we shall look at testing trends of the law for the past 12 years. Thank you for your time, and keep it the Kenyan Teacher for more reviews.